Okay, great. Okay, welcome everyone to another MCRN Colloquium. Today we're lucky to have Dr. Kristian Strommen speaking. He's both at the University of Oxford and ECMWF as a research scientist, I think 50% time, which is really cool. And he got his PhD in 2015, also from Oxford University in mathematics. And today he will be talking to us about a topological perspective on weather regimes. So with that, please take it away.
Yeah, thanks very much, Kristian, for the invitation to this colloquium seminar. So I'm going to talk about weather regimes and topology, or to use this kind of slightly exaggerated subtitle, how to save the world with topology, which is how one person kind of described this work in a kind of a slightly jokey way, and you can decide if you think this how seriously or not to take that. So this is work I've done with a few people. It started off as a kind of conversation with Nina Otter, who does a lot of work in topological data analysis, and then two of my former colleagues from Oxford, Matt and Josh. And maybe I'll say immediately that if you want to read any of the details of this stuff, then there's a paper out with the same name as this title, the title of this talk, which has all the details. Okay, so maybe I should set some context there while you kind of get distracted looking at this animation, which is that, so my background, so I did my PhD in maths, but then in like number theory-ish kind of stuff, and then I moved to climate science afterwards for my first postdoc, and I've been in climate science for 8 or maybe 9 years even now since then. And for a long time, I kind of didn't think that there was any of the maths that I did for my PhD, which was even vaguely relevant for studying climate change and weather forecasts. So it was a kind of really fun little moment when I realized, talking to Nina, that maybe there was this kind of interesting application. And there are many ways to phrase this application, but one concrete way of thinking about this is this question I put here, which is, how will mid-latitude weather change with global warming? So mid-latitudes, if you're not familiar with that, just means everything above the kind of tropical equator. So in particular, the northern mid-latitudes is what I'm really thinking about, which is what you can see on this map here. So all of North America and Europe and northern Eurasia and Russia, and so on. So there are two kind of aspects to this, or you could think about the climate change in two ways. Well, there's the kind of simple thermodynamic effect, which is just that the temperature and therefore also the humidity in the atmosphere will go up. But there's a more complicated question, which is how the dynamics will change. And that's what this animation is showing an example of, the so-called dynamics of the atmosphere. So what this is showing in particular are it's anomalous pressure at 500 hectopascal, so fair ways up into the atmosphere. So the red blobs here are positive pressure anomalies, and the blue blobs are negative pressure anomalies. So you might have heard in weather forecasting, you talk about high pressure systems and low pressure systems. So that's what these are showing, the high pressure and low pressure systems moving around and evolving in time. And if you're on the ground, walking around and experiencing weather, then it's the presence of these pressure systems which is going to dominate your felt experience, and things like and create things like heat waves. So this is really complicated, as you can just gather from looking at the animation. If you've never thought about the mid-latitude climate change, this is an incredibly complicated problem. It's trying to understand how this very complicated looking dynamics might change. So, I mean, even forgetting about how it's going to change, you can see it's difficult to even understand how to think about it at all in the first place. But there's an idea which has been around in the literature, the climate and meteorology literature for a while, which can be phrased in a very mathematical way as maybe you can find a low-dimensional submanifold of this attractor, the atmospheric attractor, which captures most of the dynamics. So some kind of low-dimensional submanifold where the dynamics, where the interesting dynamics, let's say, sits on, and therefore, if it's because it's a low-dimensional submanifold, maybe it's easier to understand. And in particular, you might hope that the response to forcing, so for example, the response to global warming, is also easier to understand for this low-dimensional submanifold as opposed to the full kind of climate system. Please stop me, by the way, at any point if you have any questions. I can't see any of you, so you just turn on your microphone and start interrupting me. Right, so yes, I mentioned this idea has been around for a while, and in the climate and meteorology literature, this idea is typically referred to as weather regimes. So weather regimes could be thought of as one particular approach to finding such a low-dimensional submanifold. And
hello.
Hello. Now, yep.
Yeah. Okay. I'm sorry. Occasionally, my webcam seems to do something funny and
okay.
pulls everything up. So I've just turned off my webcam and now I'm on my laptop, which should be more reliable. So sorry about the interruption.
Okay. No worries. No worries. And we can edit that out of the video part too, so that'll be easy.
Okay. Yeah. Great. Yeah, okay, so I was basically trying to give a concrete example of this regime framework, and here's one. You think you have two pressure patterns, the so-called positive phase on the left and the negative phase on the right. So it's a really severe kind of low-dimensional submanifold where you cut everything down to just two states, and then you just think about the atmosphere. On any day, the atmosphere is said to be either in the positive state or the negative state, and then next day it moves from one to the other or stays maybe where it is, like a Markov system. And this has been used a lot because knowing which of these phases you're in is a good first order approximation to European winter weather. So this is just one example. Yeah, and just to show, an example that this is typically associated with extremes. So if you have a persistent state, if you're in one of these kind of regime states for a long time, then often you get extreme weather. This is a now increasingly outdated example from 2020 where we had this strong negative NAO pattern on the right, and we had loads of flooding in the UK that winter as a result. Okay, I want to show you another kind of toy model, which a famous toy model for this, which many of you probably will have seen before, which is the Lorentz butterfly, where this idea of the notion of chaos was first discovered. So this is a kind of a dynamical system which was obtained by, again, doing a really severe truncation of some of the equations of motion, and you get an attractor, a strange attractor, which looks like this. And the reason I'm wanting to show you this system is because it shows a really nice property, which is that if you introduce a forcing term to these equations, so you integrate the equations the same as normal, but you add a little constant forcing every time step, then what happens is you go from the top to the bottom. So essentially, if you could just see by eye that these wings of the attractor haven't moved, but the time spent in the different wings has changed. So in this case, the forcing is pointing a little bit to the right, so you end up moving towards spending more time in the right wing. So a way of phrasing this mathematically would be that these regimes are invariant under small forcings, where I'm thinking about the regimes as the two wings, but then the temporal variability changes. So that's very nice, because if you recall that I was saying before that the sort of goal of the idea of using these regimes is that maybe the response to forcing will be simpler. And here is a kind of prototypical toy model of a regime system where indeed the response to forcing is particularly simple. It just involves a change of which wing you spend more time in. Okay, so that's great, because that gives us a potential strategy for understanding mid-latitude climate change in a very concrete way. So the hope of a dream is that maybe the mid-latitude behaves approximately similarly. So maybe all we need to do is identify the correct regimes, then show that these regimes are somehow invariant under global warming or any warming, and then but that they have some kind of change in temporal variability. And then if you have that, then you can just infer how the kind of dynamics is going to change with a certain amount of global warming. So that's the kind of strategy and idea which has been around in climate science for several decades now. And it turns out, perhaps a bit surprisingly, that the really difficult step is the first step, which is to just identify the correct regimes in some sense. What are the, with this Lorentz butterfly, it's very easy to look at the attractor and say, okay, it splits up nicely into these two wings. But in the real climate system, which is extremely high dimensional, you can't just look at it with your eyes and kind of work out what it is. And this has led to a kind of proliferation of different regime frameworks. I'm not going to explain to you what's on the slide on the right, really. I just want to make the point that the regimes idea has been around for at least 70 years, but there's still no agreement about what they are, what the definition is. And depending on your approach, you might end up decomposing the atmosphere into any number of different pieces and different ways, and they aren't all kind of easily comparable with each other. So the question is, what do all these regime systems have in common? So, okay, I've shown you the Lorentz butterfly in the bottom left. I've shown three other examples of kind of systems. So this Charney divorce system in the top left and Lorentz 96 in the top right. These are also idealized toy models that have been studied as having regimes, and I'm showing you a picture of their attractors. And the bottom right is an example from real climate data, which is not a picture of an attractor, but just a particular trimodal histogram, which corresponds to the latitude of the North Atlantic jet stream, which has also been studied as a kind of regime phenomena. But all of the kind of typical definitions that you find in literature and climate and literature, such as the ones I've kind of listed in the middle here, if you try to apply these and to all these systems, you always end up excluding one of them. So none of the kind of definitions that are around seem to capture all these different kinds of regime systems. This has kind of led to what I jokingly refer to as a regimes as pornography situation, where there's this famous court case from the 60s about what is the definition of pornography. And this Supreme Court Justice Stewart famously said that, well, I can't give you a definition, but I know it when I see it, right? And maybe it's the same regimes, and you can't really define them, but maybe in any particular examples, we can kind of know, we know them when we see them. But obviously, as mathematicians, if you're a mathematician, that's deeply unsatisfying, and that's natural to want to do a better job. And the kind of childish idea which came out of this conversation I had with Nina also many years ago was that somehow the common feature in all of these cases is that there's some non-trivial topology floating around. So if you just kind of squint and look at all these things, or you don't even have to squint in all cases, right? But in general, if you look at these, you might think that, well, it's just a bunch of loops and connected components in some sense, and that's the key structure. And maybe that means that this low-dimensional submanifold that we're looking for in the real climate system can somehow be detected topologically. So how do you do that? How do you detect something topologically? So you have to forgive me if hopefully not everyone in the audience are like topological data analysts, in which case this next bit will be trivial for you. But essentially, you use topological data analysis. And topological data analysis tries to deal with this question of how do you apply something like homology to a point cloud. So if you've got a data set like on the right, then as a space, as a topological space, it's just a bunch of discrete points. So it's a totally disconnected space and has got no interesting topology or homology or any other topological invariant. But again, as humans, we can look at this and say, well, actually, this should somehow be two connected components and a figure eight. So how can we kind of capture that? And persistent homology is the tool that's been developed. And basically, you solve this problem by introducing a filtration. So specifically, if you're starting in figure A with your point cloud, then what you can do is you can start kind of connecting points. You specify a distance parameter r, and depending on that parameter r, you will begin connecting points that are a distance of r away from each other. And as you increase r, you move along this line in figure B here. So you can see for certain parameters, you will recover exactly a space, a genuine topological space, which has the homology that you expect. And you can kind of measure then how the homology of these spaces vary with this parameter r, so a so-called filtration. And you can kind of capture that information in so-called barcodes. So that's what these blue lines and the purple lines at the bottom, they are showing the persistence of connected components and loops, respectively, as you vary this distance parameter. I mean, the idea is that, well, if you find topological features which persist for a lot of values of your filtration, then maybe those are somehow meaningful. Yeah, so the fact that you have these two long blue lines and two long purple lines is exactly saying, you know, that this point cloud has got two connected components and two loops in it in some formal way. So this was like pioneered by people like Gunnar Carlsson and then many others in subsequent years. But you run into problems immediately if you try to just apply this to the climate system or any dynamical system for that matter, any continuous dynamical system. And that's, well, there are several reasons for that, but one basic problem is that you can prove that continuous dynamical systems have connected attractors. And why is that problematic? Well, because we want to be able to view multimodality as distinct connected components. So if we take this case of where we have this North Atlantic jet latitude metric, then we have a trimodal histogram, and we want to somehow intuitively find a way of representing those three peaks as three connected components. But in a genuine continuous dynamical system, that will never happen. So if we go back to our figure 8, like this will never happen because there'll always be a kind of trajectory of points that connects the figure 8 with the point cloud on the right. So we'll never get that clean separation that we get here in a real dynamical system. And somehow the problem here is that these real dynamical systems have variations in density, and those are important, but persistent homology by itself doesn't tell you, it doesn't care about it. It doesn't care about variations in density. If the points are if two regions are connected by trajectory, then that's it, they're connected. And it doesn't matter if that trajectory is like a tiny infinitesimal line, say. So how do we deal with that? Well, the way we ended up dealing with that was just the most naive way possible. We just take the original idea of persistent homology and extend it into a different dimension. So now we have a two-parameter filtration where the first parameter is distance as before, but now we have this other parameter, which is density. So specifically, if we have a data set, a point cloud data set like what's shown at the top, then you can specify this distance to link together points, but you can also specify a density threshold where you throw away all points, where you first estimate the density at each point, and then you throw away all the points that are below a certain density value. And then you can vary both the distance and the density, and you'll get some diagram, or you get some conceptual diagram like I've shown here, wherefore, depending on your choice of density and distance, you will get the kind of expected result, which is that the main feature in this point cloud is that there's a loop, right? And then there's some outlier points that we want to kind of ignore. So that's the basic strategy here, or certainly a basic strategy, to just move from the one parameter persistent homology to a two parameter persistent homology. And that basically gives you a pipeline for studying topological features of a dynamical system. So first of all, you estimate the density somehow, and then you start subsetting. You subset to some p% densest points, compute the topological variance using regular persistent homology, and then you try to come up with some way of exploring how the topological structure varies in this two-parameter space, which I'll now show you some examples of. Yeah, so okay, the question is obviously, does this work? And I'm just going to show you a few results of what happens when you try to apply this to some of these classical regime systems looked at in the climate science literature. So the first one obviously is going to be the Lorentz 63 butterfly, where we want to say that there's one connected component and two loops or holes. So what this figure is showing is, well, in the top left, it's just all the points, like from a particular integration of this system. And then we start subsetting. We pick out only the 80% densest points. And then you can try to apply persistent homology algorithms. And if you do that, then with a bit of luck, you can find these loops. So that the loops, the kind of squiggly loops in the top right and the bottom left were detected and plotted using purely computer algorithms, right? I didn't draw them with paint or anything like that. So you can actually do this. And then as you start subsetting more and more, you kind of, the wings start breaking up. And finally, when you get to only the absolute densest points, you end up with only the kind of bit in the middle. So in order to kind of try to visualize things in this two-parameter space, it's a bit awkward, and very happy if anyone has any better ideas, but this is what we ended up doing. We ended up making plots like this. So there's some kind of information at the bottom, which is trying to deal with statistical significance questions, which I'm going to ignore. The features I want to focus on are the features, the red dots and the blue triangles in the kind of upper part of the plot. So the fact that we have these red dots continuously along the top and just one red dot at all times is telling you that in this entire kind of two-parameter filtration, you always only have one connected component. But then we also see that if we go to the right, then for a kind of range of density thresholds, we find these two wings of our two blue triangles for a range of thresholds. And then you can actually go back and check that those triangles here really do correspond to those wings that we found, that we can see. I just want to show you a quick example of what this looks like for a more complicated system. So this is this Charney-Devore system. Again, it's just a severe truncation of a subset of the equations of motion. So if you're not familiar with that kind of stuff, it's basically just Navier-Stokes, essentially. So you truncate something like Navier-Stokes very severely, and then you end up with something maybe like this. So this has a very complicated dynamics where in a regime context, you typically think of it as having two regimes, one regime corresponding to the kind of dense center where the dynamics are very slow. And then you see these big bursting loops kind of shooting out from the center. So you get what people refer to as bursting transients coming out. And the collection of loops essentially corresponds to what people have classically thought of as the second regime. So in kind of climate terminology, the dense center corresponds to a blocked flow, and then the loops are some kind of zonal flow. And again, I'm just showing this because I want to just emphasize that you can use a computer program to find these loops and color them in for you. So it's not always the easiest to visualize, but it is possible algorithmically to find these things. And again, now, of course, as you might expect, this is a much more complicated looking system. So if we do this kind of 2-parameter barcode like plot, we get a lot more complicated information, but you can kind of check that this kind of red dot that I've marked as in the 20% threshold corresponds to this dead center. And then otherwise, there's just one connected component and then a bunch of loops. So there's a bunch of blue triangles, which is telling you that there's just a bunch of loops. So if you squint at this plot, you might say, well, Charny-Devore is basically one connected component with a particularly dense center, maybe, and lots of loops. And again, you can kind of go back and forth. You can go from all these. You can go from the information on this plot back to the actual system and check what you've actually computed. Oh, I did want to show you one example from the real world. So I want to emphasize that this is not what I would say is the kind of true answer to what the regimes are in the real mid-latitudes, and I'll explain why in a couple of minutes. But this is just to show you that you can apply this to a genuine climate data set. So again, it's this North Atlantic jet latitude that I'm using here. So it's just basically, what this data set is trying to measure is something about the location and intensity of the jet stream, which you might have come across before. And so the full data set is in the top left, and this 100%. So if you include all the points, that's what it looks like. And then if you start subsetting down to the denser and denser points, then eventually it splits up into 2 components. And yeah, I won't dwell on this too much, but there's a kind of issue here I've highlighted here, which is that really we wanted to find 3 connected components corresponding to the 3 peaks of this distribution. But essentially, because of the crudeness of how we are doing this 2-parameter filtration, we aren't able to see that. We only get these 2. And for people who know something about multi-parameter persistent homology, the problem is that somehow we want to take diagonal slices rather than vertical slices in this 2-parameter space. Okay, so just to summarize then, the kind of idea here is that regimes, these things which have been studied as under the name of weather regimes for 70 years, maybe you can think about it as, or you seem to be able to measure it as topological structure, and you can algorithmically find the relevant structure using persistent homology. And it works pretty well in all these classical systems that we've looked at. And the kind of relevant classical regime structure in all cases ends up corresponding to either components or loops or holes. And in that sense, we can distinguish all the dynamics of all these systems by their homology. So does this mean that weather regimes are, people have been studying weather regimes for 70 years? Maybe it's just the fact that there's no kind of clear definition so far is because everybody has basically been trying to find in some way or another the non-trivial topology on a high-dimensional climate attractor. And depending on exactly how you try to kind of cut that topological, that non-trivial topology down to a kind of human level, you get these different weather regimes. So in order to test that, what you of course want to do is then apply this methodology I've outlined to really high dimensional climate data. So in all cases in the literature, this regime classification stuff to genuine climate data is always done on an extremely low dimensional subset. So, which is kind of like, has led to all sorts of difficulties, because you're looking for this low dimensional submanifold, but then you start off by just cutting everything down to an extremely low dimensional space to begin with, and there's obviously it's very likely that you end up throwing away a lot of important information in that sense. And this might be part of why there's been a lot of ambiguity. But persistent homology is particularly nice for that reason, which is because the algorithms of persistent homology scale very well with the dimension of the data. So after you've done some kind of initial pre-processing of the data, then you can add dimensions to the problem, and the scaling goes up just by the square of the dimension of your data set, which is much better than the typical kind of exponential growth of the exponential growth you get with just about every other method out there. So in principle, this kind of approach gives you a way to probe high dimensional climate data set very efficiently, unlike some of these other classical methods which I've listed here. Now, because this is a kind of mathematics colloquium, I wanted to emphasize some of the kind of more interesting mathematical problems which seem to come up when you try carrying out this strategy. One really interesting problem is this question of statistical significance. So if you imagine trying to do this with real atmospheric data, real climate data, then of course it's a noisy data set. There's all sorts of, it's a chaotic system. So there's going to be noise everywhere. And if you want to try to kind of see how, say you want to see how a topological structure in the atmosphere has varied over the last 100 years or something, there's guaranteed to be some changes which are just due to noise. And you have to be able to say, which changes in the topology is somehow real, which gets you straight into statistics. And there's a lot of interesting work actually on trying to do statistical significance stuff for persistent homology, which it's a very active and ongoing kind of area. There's also questions about somehow doing this multi-parameter filtration, this two-parameter filtration, or what I'm calling here bifiltration, how to do that in a kind of quote-unquote continuous way, by which I mean somehow preserving information across this barcode. So just to give you a concrete example, if we go back to the Lawrence 63 butterfly, so if you look at these blue triangles on the right, then you can kind of believe that the two blue triangles always correspond to two of these wings. But if you go from like the 80% line to the 90% line, then there's no way to kind of match, there's no a priori way to match any of these things up with each other. They could in principle be completely different features from one kind of slice to the next. And I think there's a lot of interesting questions about how to improve that situation and try to preserve some of the information across this filtration. And then the third kind of open problem is a more kind of dynamical systems problem, which is that, say you go the other way around, say that now that you've got some topological features of on the attractor of your dynamical system. Well, what actually can you infer about the dynamics of the system? And to give you one example question, concrete question, suppose you know that there's a loop in some sense, and you found that there's a long-lived loop using homology. Does that mean that there is, or when does that mean that there's a quasi-periodic orbit in your system? Okay, so that takes me to my conclusion slide. So to summarize, persistent homology and kind of adaptations of it give you a novel way to try to look for a low-dimensional submanifold. and you can, in theory, use this to study climate change. And this is there's a lot of work in progress going on where we are trying to extend this this kind of pipeline to genuine high-dimensional climate data. But I want to emphasize that there's really, climate scientists don't know anything about algebraic topology, right? So there's a million places in climate science where you could think about applying these kind of techniques. And some of the people who came to this AMS summer school last year have indeed started to do that. And maybe some of you might be inspired to do the same. So thanks very much.
Okay, great, thank you. That was a fascinating talk, absolutely fascinating. And yes, everybody can click the clap emoji for Kristian. So yeah, I guess if you have time, Kristian, I know you said you might have limited time, but if you have time for Kristian.
I'm happy to take questions for at least 5 minutes.
Okay, yeah. So if anybody has a question, please go ahead. KK, sure.
Hello, it was a very nice talk, very clear, and I also like very much you're trying to use topology on a high-dimensional system to extract the weather regimes. I was involved in the weather regime research ever since the beginning. My involvement was to say why their approach was wrong. Chani was disappointed with me when I showed that his weather regimes, when you increase the truncate, they obtain those by truncating a large system, PDE, into a small subset of Fourier components. But when you include more and more components, it disappears. Similarly, Lorentz, which is used as a conceptual model, the regimes also disappear if you include more and more components, because the Lorentz system is also a truncation out of a Rayleigh-Bernard convection, which is a PDE. And Reinhold Pierre Hamburg sort of followed Lorentz and used two-layer model and created these weather regimes, which also show that when you include more components, it's all gone. So the approach is not to, as you mentioned, there are approaches where you just don't look at the other dimensions, just focus on the field. And that is not the approach. The approach is to use a large system and then try to extract relevant sort of low dimensionality. I was wondering in that regard whether a method called empirical mode decomposition, empirical orthogonal functions, which was actually invented by Lorentz and is used extensively by Maya Wallace and others to extract the relevant low-dimensional EOFs in the high-dimensional data. And that method actually was based on the percentage of variance included in that particular low-dimensional system. And that's sort of like your density type of filtration. Yeah. So, and there have been, over half a century of such work. So some of those identified EOF has been shown to be relevant to atmospheric phenomena, right? So, ENSO, PDO, AMO, AO, etc. So perhaps that could be a better initial sort of clue to look for low dimensionality, because you're given a whole high dimensional system and it's really hard to know where to look. That is better than truncating. Yes, and then those Atlantic jets ones, if they were not obtained from EOFs, then it's like they're throwing away a lot of things, but EOFs is a rigorous way of obtaining those.
Yeah, thanks for your comment and for making it clear who you are. So now I obviously know who you are now. So it's great by you. Great, it's great to have you here in the audience.
Yeah.
So basically, I agree with a lot of what you said. I think using empirical orthogonal functions as a kind of initial step is probably going to be important when you try to apply this for a high dimensional system. My guess or instinct is that the key thing is really to begin to introduce several different variables, right? So if you think about the dynamics of the jet stream, it's not like typically it gets studied either only using wind data or only using pressure data, and maybe you do some EOF decomposition, but you stick with one variable. But a lot of the dynamics is actually about the interplay of winds, pressure, and temperature, and how the build up and release of barotonicity and stuff like that, which you need several variables in order to begin to really capture. So I think what we're trying to do is essentially do some, bring in multiple climate variables and then do a quite generous EOF decomposition and then try to apply these kind of techniques and hope to really begin to see some non-trivial topology.
Thank you.
Okay, maybe we have time for just one more quick one if anyone has one. Okay, if not, we'll let you go, Kristian. So I know you were a little time limited. I really appreciate the talk. It was absolutely fascinating. And we should have a talk next week as well, and hope to see everybody there.
Well,
Great, Thanks again for the invitation. I'm sorry about the tech issues.
No worries.
You can edit it out.
Perfect.
All right.
See you again, Kristian.
Oh, hi, Seth. Yeah. Bye now.